Hello everyone. Today we are going to be looking at the central case study for Chapter 15 as well as real data for Chapter 15. Let's start with the central case. Please go ahead and turn in your workbooks to page 280 and 281, where we're going to be reviewing how charging towards clean air in London. As you can see, the sign warns London drivers that they must pay a fee to drive in the central city. And this is for to reduce congestion in the area and hopefully ultimately reduce the amount of pollution. Let's read through the central case together. Air pollution is not a new problem in the City of London, England. Even during the Middle Ages, pollution from coal burning was widespread. During the International Revolution in the 18th and 19th centuries, the use of coal grew. Coal fired the nation's industries, heated people's homes, and polluted the city's air. In December 1952, weather conditions trapped pollutants over the city for days, creating a thick, killer smog. Londoners breathed the heavily polluted air. Many people became sick. The smog was especially dangerous for people with respiratory or heart problems. The killer smog killed at least 4,000 people, and by some estimates, as many as 12,000 people. The disaster spurred Great Britain and other developed nations to take steps to control air pollution. Today, Londoners breathe much cleaner air than they did in 1952. Burning coal is no longer a major source of pollution in the city. However, Londoners still battle the pollution released by motor vehicles. About 250,000 vehicles commute into London's downtown area every workday. And these cars and trucks spew out air pollutants. Ken Livingstone, a mayor of London, developed a plan to charge drivers a fee for entering the city. He thought that this measure could reduce traffic congestion and might also reduce air pollution. In February of 2003, London's congestion charging program began. People driving into central London on weekdays began to pay a fee every day. The money has gone to improve bus service and encourage people to travel by rail, bicycle, and foot. Many Londoners have been outraged by the program. Some daily commuters complain that the fee is too high. People also argue that the system discriminates against poorer people who cannot afford the fees. Many other Londoners, however, have supported the program. Since the program began, traffic congestion has decreased by nearly 30%. Fewer cars are now entering the congestion charging zone in central London. Londoners in the zone have suffered fewer injuries from traffic accidents. It has been difficult to assess the effect of London's congestion charging program on air pollution because it is hard to determine the cause of any change in air quality. A reduction in pollution could be the result of the program, but it could also be caused by some other factor, such as improved vehicle technology. Measurements after 1 year showed a decrease in some pollutants in London's air, but a study in 2009 indicated that little overall change in air quality. Several other cities, including Singapore and Toronto, have adopted a congestion charging program similar to London's. More cities are considering such a program, hoping to reduce both traffic and pollution. Now, if you would, I'd like you to read through Charging Towards Cleaner Air in London, page 280 in your workbook, and answer questions 1 through 6 on page 281. Let's review the major points of the article. More than 4,000 people in London died during the event, Killer Smog Event, in 1952. In 2003, London started charging a fee to people who drove into the city during the week. Since the program began, traffic congestion in London has decreased by 30%, but there is not a lot of evidence that air quality has improved. What do you think? What are some of the pros and cons of a congestion charging program? And would you be interested in seeing one adopted by your local community? Now we're going to take a look at real data. And we're going to look at the firsthand effects of the Clean Air Act. The Clean Air Act had major effects on quality of air we breathe. To monitor air quality, the EPA tracks emissions of several major air pollutants. The graph shows data for some air pollutants: carbon monoxide, nitrogen oxides, volatile organic compounds, sulfur dioxide, and lead. Look at the graph and then answer the following questions. We're going to go through this together. Number 1, interpreting the graphs. What do the green bars represent? To answer this question, we need to look at the key. The green bar represents the amount of pollutants emitted in 1980. Number 2, interpret graphs. What do the purple bars represent? Again, just like for the green bars, we're going to look at the key on the graph to answer this question. The purple bars indicate the amount of pollutants emitted in 2008. Number 3, analyze data. What trend does the graph show? For this, we want to look at the difference between the amount of pollutants emitted in 1980 versus the amount of pollutants emitted in the year 2008. And we're going to look at these for each of the 5 major pollutants. And we can see that in each case, the amount of pollutants has been reduced. So we would say the amount of pollutants emitted into the air has decreased since 1980 for all 5 of the major pollutants. Number 4, analyze data. Of the pollutants shown on the graph, which has changed by the greatest percentage? This one's pretty easy and straightforward because they have provided us with the amount of reduction between the years 1980 and 2008 for each of the pollutants. So we just need to look for which of the components or pollutants had the largest decrease, and that would be lead. There has been a 99% reduction in lead pollutants. Number 5, interpret graphs. Why is the bar for lead shown separately from the bar from the other pollutants? Hint, we want to look at the axis labels. So if we look at our x-axis, we see our pollutants listed out. And we see that we have 2 y-axes. So why are they separate? Well, the y-axis of carbon monoxide, nitrogen oxide, volatile organic compounds, and sulfur dioxide is represented in mass emitted with a variable of millions of tons. Or our units are in millions of tons. When we look at lead, lead has its own y-axis, and it is measured in thousands of tons. So the amount of lead is given in thousands of tons, while the amounts of the other pollutants are given in millions of tons, which requires separate y-axis labels. Number 6, infer. Do you think that the general trend shown in the graph is also true for the air in London between 1952 and now? Explain your answer. Well, I would say yes. And that's because after the smog catastrophe in 1952, London took extreme measures to curb their air pollution. So we would expect a decrease in the amount of pollutants found in their area. Go ahead and turn in your workbooks to page 278. I would like you to go ahead and read through the effects of the Clean Air Act with this graph and answer the additional questions 1 through 5. When you're done with that, you can return to the lecture for a short review. Now that you've had some time to fill in your answers, let's discuss them. One, what does the x-axis represent? Well, like we discussed in the last slide, the x-axis is representing the different types of air pollutants. Next, what does the y-axis represent? Again, we discussed this in the previous slide. The y-axis are the vertical axis. One is provided for the majority or for pollutants, which is the mass emitted by units using millions of tons. Lead is listed separately in that its y-axis is mass emitted in the units of thousands of tons. So we would say the y-axis represents the mass of pollutant emitted. Number 2, study the key. For each pollutant, what does the green bar, white bar, and value in parentheses mean? Well, of course, just like we did before, we're going to refer to our key. The green bar represents the amount of pollutants emitted in 1980. The white bar represents the amount of pollutants released in 2008. And the value in parentheses indicates to us the percentage change in the amount of pollutants emitted between 1980 and 2008. This allows us to easily be able to identify which pollutant had the most significant reduction, lead, or ones that have a less significant reduction. But still, you can see after the Clean Air Act that all emissions have gone down. Analyzing data. When a percentage change is positive, it indicates an increase. When a percentage change is negative, it indicates a decrease. Number 3, 1980 to 2008. Did the amount of carbon monoxide in the air increase, decrease, or remain the same? So we want to go to our x-axis, locate carbon monoxide, follow it up, find our percentage change, and look to see if it is positive or negative. It is negative, which indicates that there was a decrease in the amount of carbon monoxide emissions. Number 4, notice all the percent change values on the graph are negative. What does that indicate about levels of the 5 pollutants in the air during the period from 1980 to 2008? We can summarize this by just stating that emissions of all 5 pollutants have decreased. Number 5, which pollutants showed a greater decrease in emissions in 1980 to 2008? Nitrogen oxides or sulfur dioxide? So first, since we are looking at decrease, they are all decreased because all of the values are negative. And now we need to determine which one has the most significant decrease. And we are only comparing nitrogen oxide with sulfur oxide. So you need to determine which one has a greater decrease. Is that going to be nitrogen oxide with -40 or sulfur dioxide with -56? Well, since -56, 56 is a greater number, it indicates that it had a more significant decrease. So the answer is sulfur dioxide.